who's going to talk to us about star formation in the early universe and Bayesian statistics.
Yeah, I'm going to skip the Bayesian part today. Yeah. Yep. Thank you for that. And thank you, everyone, for letting me be here this week. This is my first time. I'm already having a great time. So that's a big positive. I'm Justin Cole. I work with Casey Papovich. And today what I'd like to talk about is trying to disentangle star formation rate timescales using Sears, and then kind of looking at the duty cycles of star formation in the early universe. I did not label any of my figures in this talk, but any unlabeled figures can be found in my paper from this year. So the motivation for this is basically to study scaling relations. As was said before, we love drawing lines on stuff, and we've drawn lines on star formation rate versus luminosity or stellar mass at redshift 0 using millions of galaxies in SDSS. We've done this out to roughly redshift 2, 2.5 using medium band surveys, and we've attempted to push this out to high-ish Z using surveys like candles. But the problem is that we run into these low number statistics, and that's really where the Sears survey kind of allows us to enter this higher redshift regime. And it being in the candles and EGS field, we have coverage from HST with partial coverage in F105, and then we have full near-cam coverage, including 410 medium. And our fiducial catalog in the Sears data releases have roughly 100,000 galaxies. We've got about hundreds, on the order of hundreds of spectra above redshift 4.5, and that will I'll kind of come back to that at the end of my talk. But the regime that we really want to focus on here is this redshift 4.5 to 12 redshift regime. And this is really nice because not only do we have Lyman breaks for all galaxies past redshift 4.5, we also have more than 3 photometric points that span the UV at all redshifts, so we can get a good indication, or we have good markers for longer star formation timescales using the UV. And then we select a few more things. We do 2 more selections. Basically, we want to require that the HST and JWST photometry are consistent with each other. If they're not, it's going to make SED fitting extremely difficult. So that's one selection that we make here. And another is the width of the redshift distributions that come out of EZ. And we essentially want 70% of that redshift distribution to be contained within about 1/2 of 1 plus Z. So we want relatively well-constrained redshift distributions, and as you go to higher redshift, as you can see, those distributions are allowed to get broader. So I'm going to start with SED fitting. I've kind of mentioned that we have good Lyman alpha breaks for many of the for all galaxies in our sample. And so what I'm showing here is my favorite kind of corner plot, where it's not like everything vomited everywhere, but just the important things. And then I'm also showing you the best fit SED in the top right, and the star formation history. And I'll talk a little bit about the blue and red in a second here. But I want to focus on this. As I mentioned, strong Lyman alpha break. But the biggest feature that we started to notice in many of many of the higher redshift Sears galaxies is this elevated flux where we would expect to find optical emission lines. And essentially what that does is it allows us to measure star formation on some slightly different timescales. And so what we can do is we can use the UV luminosity and the UV slope to constrain star formation on roughly 100 megayear timescales. So that's just the integral of the star formation history over 100 megayears. But we can also, I would like to argue that we can also trust shorter timescales because we have these elevated emission lines in the photometry. So we know that these emission lines are present, and at higher redshift, many of these should be hydrogen, oxygen lines that we're seeing, and they should be coming from star formation. It should mention that the last selection we do is an X-ray AGN luminosity X-ray cut, but we only find 3 X-ray luminous AGNs, and we know that it's not super efficient at these redshifts. It's something that we're dealing with in the referee report, so we'll have more information later after we finish that up. So I want to talk about 3 primary cases where what we're seeing is we're seeing galaxies that sort of sit up above the star, what we would nominally call the star forming main sequence. And in the top right panel there, you can see that is the yellow square is where the galaxy that I'm showing on the left lives on the star forming main sequence. And you can see if I take the 100 megayear star formation rate, it's going, when I integrate over those 100 megayears, it's going to drop, even though the star formation history shows that it is rising. But I can actually constrain that rising star formation history if I integrate over 10 megayears. And so this is basically what we are looking at is what galaxies have a case where star formation rate is rising. Star formation rate is rising as a function of time. Star formation rate is relatively flat as a function of time, at least over those 10 and 100 megayear timescales. And finally, where we have a drop in star formation right before the epoch of observation. So these are the 3 cases that we want to focus on here. The case where you have really rising, a flat, or a declining star formation history. And this is motivated by the star forming main sequence when measured over 100 megayears versus over 10 megayears. These are split up into a number of redshift bins. And you can see that it's roughly consistent with some of the redshift 5, redshift 6 measurements that have been made. But it is consistent with some of the results that are coming out from JADES. And that's really, that makes me feel a lot better, is that the CIESLA data is roughly lining up with ours. We're using different data sets. So these are all good check marks, if you will, for our sample of galaxies. But the thing to notice here, and to me it's glaringly obvious, is the amount of scatter that we're seeing in the star forming main sequence. And this scatter is basically what drove this entire paper. But it's not immediately obvious why this should be the case. But just to go over some of these results really quick from our MCMC analysis, when we look at the 10 megayear star formation rates, we see a static normalization, but an increase in sigma. And that's not something that we should see, that we would expect from lower redshift studies. And this is really what I have focused almost the last year and a half on, is that blue line, that increase in sigma, the intrinsic scatter of the star forming main sequence. So as I said, we are finding that on 10 megayear timescales, the normalization is roughly static. Sigma appears to increase as a function of redshift. And on 100 megayear timescales, we're seeing that beta is increasing with redshift as we would expect. And sigma is roughly static, again, as we would expect. And yes, OK. So we first look at the dispersion in star formation. So instead of measuring the intrinsic star formation during the MCMC process, we just estimate 1 sigma scatter, assuming that the distributions are Gaussian. And we see that on 10, those are the square points with the colored lines through them are our 10 megayear, the 10 megayear star formation rates. And so we can see that at higher stellar masses, especially at high redshift, we tend to get an increase in the scatter along the star forming main sequence. I don't want to put too much into that. This could be selection bias, since we can't see, faint things are hard to see. So we could just be missing galaxies that are not currently forming stars at lower masses. But when we look at the distribution in specific star formation rate, we can see this clear separation between galaxies with low mass, which is the top panel, the darker blue line, and galaxies with higher mass, which is the bottom panel with the darker red line. And I've just included both, so it's easier to see by eye. And so what this kind of tells us is that the distribution of these galaxies might be very different in specific star formation rate space. And it turns out that that's kind of true. So on the left, I'm showing the distribution of specific star formation rate on 10 megayear timescales for my low mass sample of galaxies. And on the right, I'm showing the same for the high mass sample of galaxies. And the bars just show the mean of the peaks of the fits. So on the left, we felt that it was reasonable to do a single Gaussian fit to these, with the exception of the 4.5 to 5 bin, although there is an overdensity at redshift 4.7 in the Sears sample, so this could be affecting those results there. But you can see that there is this population of galaxies that's kind of required at higher masses to explain this increase in the width of the star-forming main sequence. And so that would be the red bar on the left, or the second Gaussian fit on the left-hand side of these distributions. And so we looked at the ratio of star formation rates. So if we take SFR10 minus SFR100, and we look at that ratio, what we can see is that at higher masses, that there are more galaxies that tend to have lower star formation rate on 10 megayear timescales and higher on 100 megayear timescales, or what we are going to call napping galaxies. And so when we look at the actual fractions, the low mass sample does tend to kind of just sit around 50%. 50% of galaxies are active, 50% of galaxies are napping. But when we look at the high mass sample, what we're finding is that almost 60 to 80% of galaxies are in this napping phase, or 20 to 40% are in this burst or active phase. And so, here we go. And so we get to the duty cycles, and just a few things to point out here. When we look at the duty cycle of star formation for the high mass sample, using a simplified model here, we can see that most of these things have duty cycles on the order of 60-ish megayears. And then when we move to the low mass sample, we can see that these timescales are a bit longer. And so what that what we think that means is that these feedback-free starbursts are essentially occurring faster or more, we're catching them in the higher mass galaxies, and we just don't see, we see a much longer timescale of star formation for lower mass galaxies. But it does appear that these massive systems are where these feedback-free starbursts are occurring. And I think we've had a few talks today that have talked about that a little bit. So some conclusions and what we plan on doing next, and I apologize for how fast I just screamed through this, but we see that there's kind of, what we expect from local relations on 100 megayear timescales is what we find at higher redshifts. We see it, the normalization going up and the slopes potentially flattening, but this smooth transition kind of breaks at high redshift, where it becomes, where we think our claim is that galaxy formation becomes much more variable. And yeah, the next plan is to actually make this into a three-dimensional problem as opposed to a two-dimensional problem, where redshift uncertainties and uncertainties in basically all of the parameter spaces can be used in our MCMC routines. And then we also want to look at the conditional mass functions, conditional UV luminosity functions, conditional star formation rate functions, because they should be related. They should all go together. And hopefully that will be the next paper in my thesis. But we know how that goes.
Awesome. Let's thank Justin. One very fast question before we go to discussion.
So my question is that I'm wondering how much of the difference in the scatters between these two star formation rate measurements on different timescales is due to our ability to measure these two star formation rates precisely.
Yep.
In just using SED fitting. For example, if you perturb the star formation history, how sensitive would how much fractional change would you cause in the star formation rates measured at these two timescales?
Right. That's a great question. It's something that we haven't tested, but we have tested perturbing the photometry, basically treating the error 2 times the error on the photometry is 1 sigma, and then resampling the photometry and refitting. And you can get up to 20 to 50% increase in star formation on both timescales. But and that's, if you draw photometry that is all goes up, then you would expect all of your values to go up. When you draw a mixed bag, it makes redshift uncertainties much larger, so you get kind of a much larger uncertainty on those. So we've kind of sort of tested it, but not the star formation histories themselves. But the star formation histories should be coming from the photometry itself, right? It should be.
Sorry, I think we're gonna
Yep,
have to
no worries.
Move on to the discussion. But let's thank Justin again. I'll pass it to Crystal and Bottom.